Hey, today we're going to throw rocks and drop balls. It's going to be great. And if you recall, early in the semester, we were dropping balls off of one of the two tallest buildings in Worcester. And we started off with a position or displacement function. Displacement is the physics term for it, that we usually call S of t. Where t is, of course, time, and then we determined that the velocity is the instantaneous rate of change of the position, which is another way of saying that the velocity, v of t, is the derivative of the position function. And you can go a step further and say that the instantaneous rate of change of the velocity is the acceleration, a of t, making it both the derivative of the velocity and the second derivative of the position. And the beauty is, if you're dropping balls or throwing rocks on the surface of the Earth or near the surface of the Earth, then the acceleration is due only to the force of gravity. And since the mass of the Earth stays the same, the acceleration due to gravity is constant, and it's 32 feet per second, usually written as 32 feet per second squared, or in MKS units, 9.8 meters per second squared. And I'll usually remind you of those values when we're doing a problem, but it's your job to remember that gravity points down. And so when I tell you that the acceleration due to gravity is 32 feet per second squared, you have to realize that that means that the acceleration function is equal to negative 32, because it's 32 feet per second squared in the downward direction. This is my cousin Alec. And I show you this picture because, first of all, I'd like you to know that he's doing great. This picture was taken just a few years ago, many years after the story I'm about to tell you takes place, and also because it's such a great picture. So when Alec was in college, so maybe about your age, he joined the outing club, and one day they hiked up some mountain, and they got to the top of the mountain, no problem, and on the way down, Alec and some of his friends decided that rather than go down the path, they would find their own way down the mountain. And here we have Alec and his friends finding their own way down the mountain. And yes, you guessed it, Alec is this one right there. And to keep a short story relatively short, Alec fell over this cliff right here and landed right there on this ledge on his head. And even though it's about to make such great calculus, I wouldn't be telling you this story except for the classic conversation that came next, which was Alec's good friends yelled down to him, "Alec, don't move," which is pretty good advice. To which Alec gave the unforgettable response, "I'm just going down to the corner for a cheese babka," and walked off the cliff and fell the remaining distance all the way to the ground. And before we continue and do the calculus and figure out how fast he was going when he hit the ledge, let's remind ourselves that Alec is fine, so nothing to worry about. And by the way, you can tell that I didn't make up this story, because if I had made up this story, then the distance from the top of the cliff to the ledge would not be the same as the distance from the ledge to the ground. We would first compute how fast he was going when he hit the ledge, and then I would have you compute how fast he was going after he fell off the ledge and hit the ground. But they are the same distance. He fell 200 feet in 100-foot increments, and I am not going to bend the truth to my own purposes. So let's compute how fast Alec was going when he landed on the ledge. The acceleration is the instantaneous rate of change of the velocity, which is the same thing as saying that the velocity is the antiderivative of the acceleration. In other words, the velocity function is the integral of negative 32 with respect to time. And that's a very easy integral. You get that the velocity as a function of time is negative 32t plus some constant. And if you plug in the time t equals 0, you get that the velocity at time 0 is negative 32 times 0, which is just 0, plus the constant, which is to say that that constant is the velocity at time 0. And so we usually write this velocity function as velocity is negative 32t plus v0, where v0 is the initial velocity, or the velocity at time 0. In this particular case, Alec just stepped off the cliff. You can imagine that at time 0, he was going 0 feet per second. So our initial velocity is 0. We are dropping Alec off the top of the mountain here. And then if you recall, the velocity is the instantaneous rate of change of the position, and that makes the position the antiderivative of the velocity. And so in this case, we have that the position is the integral of negative 32t with respect to time. And that's an easy integral. We get that the position function is negative 16t squared plus some constant. And just like with the velocity, if you plug in the time t equals 0, you get that the position at time 0 is negative 16 times 0 squared, which is 0, plus a constant, the c, meaning that that constant c is the position at time 0. And so we usually write that as negative 16t squared plus s0, where s0 is the initial position, the position at time 0. And what is his position at time 0? Well, it's sort of up to us, but we may as well call the ground level, the base of the cliff, position 0. So at time 0, Alec is 200 feet above the bottom of the cliff, so his initial position is 200. And now we're ready to ask ourselves the key question: how fast is Alec going when he hits the ledge? And the first step in answering that question is determining at what time does he hit the ledge, because if we had a time, then we could just plug it into the velocity function and we would be done. And hitting the ledge is a question of where his position is, and the ledge is at position 100 feet off the ground. And so what we have to ask ourselves first is, when is his position, when is s of t equal to 100? And that's when 100 is negative 16t squared plus 200, because negative 16t squared plus 200 is s of t. And it's not hard to solve that equation for t. We get that t is positive or negative 5/2, or 2.5. That leaves us with two possibilities. The first is that Alec falls off the cliff, and 2.5 seconds before he falls, he hits the ledge. Well, that one doesn't make any sense. And so we have to choose the other one. 2.5 seconds after he falls off the cliff, he hits the ledge. We're now in great shape to figure out how fast he was going when he hits the ledge. We just use our velocity function that we figured out over here and plug in 5/2. And we determined that Alec was going negative 80 feet per second, or 80 feet per second in the downward direction. And that's kind of a dissatisfying answer because we don't really have any intuitive feel for how fast 80 feet per second is. We don't think in terms of feet per second. And so it would be nice to be able to convert that to something that we do have an idea about: miles per hour. And I'll just show you the calculation quickly, just in case you haven't ever seen this before. It's very easy to convert units. Notice that each of these things that I'm multiplying by is 1. 60 seconds divided by 1 minute, that's 1. 1 mile divided by 5,280 feet, that's 1. You can always multiply by 1 without changing anything, but the beautiful thing in here is how the units cancel. The seconds cancel with the seconds here. The minutes cancel with the minutes here, for example, and the feet here cancel with the feet here, and you end up with something whose units are in miles per hour. And you plug that into a calculator, or else you struggle through the arithmetic on your own, and you find that he was going about 54.5 miles per hour when he hits the ledge, so he was booking. I should say that it's not exactly true. These problems that we're doing are idealized in that we're neglecting air resistance. Air resistance slows things down, so in reality he was going slower than that, but it's also extremely complicated. It's based on the shape of the thing that's falling, the material that it's made of. Was he wearing a cotton shirt or something made of polyester? It would make a difference. And so we generally ignore air resistance and come up with this idealized value. And before we move on, I would be remiss if I did not mention that there is a moral to the story here. Take the path down the mountain. Okay, for the second in our series of bad idea experiments, we have a pistol on the ground that is fired straight up. The bullet leaves the gun with an initial velocity of 1,000 feet per second. Neglecting air resistance, we're going to answer these 3 questions. How high does the bullet go? How long before it hits the ground? And how fast is it going when it hits the ground? As usual, we start with the acceleration due to gravity, which is 32 feet per second in the downward direction, so negative 32. The velocity is the antiderivative of the acceleration, and that makes the velocity negative 32t plus a constant, and the constant is the initial velocity v0. And we're told that at time 0, the bullet is leaving the gun at 1,000 feet per second going up, and so the initial velocity is a positive 1,000, making our velocity equation v of t equals negative 32t plus 1,000. And since the velocity is the derivative of the position is the antiderivative of the velocity, and so the position is the integral of negative 32t plus 1,000 with respect to t. Which gives us that the position is negative 16t squared plus 1,000t plus the initial position, s0. And since the initial position is on the ground, that's position 0, and so we have a position function negative 16t squared plus 1,000t. Now that we've worked out our velocity and position functions, we're ready to start trying to answer the questions that were asked. The first question, how high does the bullet go? Well, the calculus way of thinking about this is we're looking for a maximum of the position function. How do you maximize a function? You take its derivative, find the critical points, and then find the ones that are relative maxima. And the derivative of the position function is negative 32t plus 1,000, which is the velocity function. And you set that equal to 0 and solve for t to find the critical points, and you find that there's a single critical point at 125 fourths, or 31 1/4 seconds. It's easy to see that this critical point is a relative maximum because the second derivative of the position function is the acceleration function, which is negative 32 everywhere. And so even in particular at t equals 125 fourths, the second derivative is negative, and so there's a relative maximum. But we still haven't answered the question, how high does the bullet go? We've just answered the question, at what time does the bullet reach its maximum height? How do we figure out how high the bullet is at that time? Well, we have a function, the position function, that tells us where the bullet is at any given time. So plug 125 fourths into that function, and we'll get how high the bullet is at that time. I want to make the arithmetic as easy as possible on myself. Well, the 4 in the denominator here, when you square it, 4 squared is 16, and that will cancel with this 16. And 1,000 over 4 is 250, and so it simplifies to this expression right here. And 250 is 2 times 125, and so this expression right here turns into 2 times 125 squared. And 2 times 125 squared minus 125 squared is just 125 squared. And there's no way around it now. I have to do some arithmetic, and I find out that the bullet reaches a height of 15,625 feet. And since there are 5,280 feet in a mile, this is just under 3 miles. Okay, I've answered the first question, how high does the bullet go? Now I'd like to answer the next question, how long before it hits the ground? I need to make myself a little bit of room. And the question of when does the bullet hit the ground, that's a question of position. The position at the ground is position 0, and so this is asking when is the position equal to 0? And to answer that, we set the position function equal to 0, and we solve for t. And when you do that, you factor and you solve and you get 2 answers, t equals 0, which makes some sense. The bullet was on the ground at t equals 0. That was at the instant that we fired it. Not really the interesting point. The more interesting point is when t is equal to 125 halves, or 62.5 seconds. So that answers our second question. The bullet hits the ground after 62.5 seconds. And then the third question, how fast is the bullet going when it hits the ground, is just a matter of putting in this time that we just figured out into the velocity function. And so you calculate v of 125 halves, and when you do the arithmetic, you get the answer negative 1,000. Which is to say that when the bullet hits the ground, it's going 1,000 feet per second in the downward direction, which is kind of nice. There's a beautiful symmetry there. It left the gun going 1,000 feet per second in the upward direction, and when it hit the ground, it was going 1,000 feet per second in the downward direction. Which is also to say, by the way, that if you really did this extremely stupid experiment and were really able to shoot the bullet straight up, then, 62.5 seconds later, it would be like you were holding a gun right at the top of your head and firing it directly down. So this is a very, very bad idea. Of course, as we said at the beginning, we're neglecting air resistance, so in reality, it would be going slightly slower because of air resistance. I don't know how much slower. Still, do not try this at home. On the other hand, do try this at home. A rock is thrown straight down from the top of a 440-foot cliff with an initial velocity of 8 feet per second. Try to determine how long before it hits the ground and how fast it's going when it does hit the ground. When you're working on this problem, don't forget that the rock is thrown down in the downward direction at 8 feet per second. So pause the video, take a few minutes, work on this problem, and when you're ready, start it back up again. Okay, these problems all start the same. The acceleration due to gravity at the surface of the Earth is 32 feet per second in the downward direction, and so our acceleration function is a of t is equal to negative 32. The velocity is the integral of the acceleration, and when you integrate negative 32 with respect to time, you get negative 32t plus the initial velocity, plus an arbitrary constant, or a not so arbitrary constant, a constant, that is the initial velocity. And hopefully you caught on to my not so subtle hinting that the initial velocity of 8 feet per second in the downward direction meant that v0 is equal to negative 8. And so the velocity function is negative 32t minus 8. And the position is the integral of the velocity, so we get that the position function is negative 16t squared minus 8t plus the initial position, s0. And since we're starting at the top of a 440-foot cliff, the initial position is 440. And now we have our position and our velocity functions, and we're ready to start answering the questions. How long before the rock hits the ground? That's a question of when is the position at the ground? The position on the ground is position equal to 0, and so that's a question of what is the time, t, when the position is equal to 0? And so we set the position function equal to 0 and solve. Each of these terms has a factor of 8, so we can pull that out. And personally, I like pulling out a negative 8 so that my initial term here, 2t, is positive. That will help me factor the 2t plus t minus 55 that I'll be left with. In other words, dividing both sides by negative 8, we have to solve this equation. 0 equals 2t plus t minus 55. And you can go straight to the quadratic formula if you really need to, but the quadratic formula is complicated. You both have to memorize it properly, and then you also have to compute it properly, and I've seen mistakes of every sort. It's always easier if you can factor, so let's take a stab at factoring. And it turns out that 2t plus 11 times t minus 5 works. 11 times negative 5 is the negative 55, and then we've got 11t and negative 10t, and that gives us the t over here. And solving this equation, we get that t is either negative 11 halves or 5. The first answer says that we throw the rock, and 5.5 seconds before we throw it, it hits the ground. Well, that makes no sense. The second answer says that 5 seconds after we throw it, it hits the ground. That sounds a lot better. And we just answered the first question. It hits the ground after 5 seconds. We're now in great shape to answer the second question, how fast is it going when it hits the ground? We just plug 5 seconds into our velocity function. And after we do the arithmetic, we get the answer of negative 168. That's our second answer. The rock is going 168 feet per second in the downward direction. Okay, that was motion. Some of you have learned other ways to do this in your physics class. I caution against it for 2 reasons. 1, if you make mistakes, I can't see where you made them and it's very hard to give partial credit. And 2, the techniques that you've learned tend to work, just on the surface of the Earth. I could very easily move these problems to the surface of Venus or Mars or some other strange planet where the acceleration due to gravity is different. And then your formulas that you may have memorized won't work anymore. Similarly, we could give some function that describes the acceleration due to gravity. I believe there's a problem like that on your homework, and then anything that you've memorized from a physics class won't work anymore. So sort of stick with the idea that the velocity is the derivative of the position and the acceleration is the derivative of the velocity, making the position the antiderivative of the velocity and the velocity the antiderivative of the acceleration, and you can't go wrong. All right, well, I guess you probably can go wrong, but try not to go wrong. As I sort of mentioned there is homework on this. Have some fun with it as usual, and also as usual, I look forward to seeing you in class.